Hello, this is video 17. And last time I left you hanging with that ridiculous notion that anything a computer could do could be done with nothing but and or and nots. And or and not. Are what we call logically complete. And spell it correctly. Oh no, I don't have anything to do addition, subtraction, multiplication, all that stuff. Basic arithmetic stuff. Well, believe it or not, I can build it with and or and nots. That just doesn't seem right. It just doesn't. I'm going to express my outrage here as an observation. How can this be? Question mark, exclamation point. For example, we don't even have an equivalence gate. We can't tell if two bits are equal to each other. We don't even have an equivalence gate. Equivalence. We can't even spell it. And we yell that. We don't even have an equivalence gate. So, build one. Now, this will be backwards. Since we don't have the gate, we start with what we want the gate to do. In other words, we'll describe its behavior. I want it to have an output of true or 1 or on when the inputs match. Unfortunately, even though that might make some sense in English, it doesn't make any sense when we're trying to design the gate. How do we actually describe it? Truth table. Truth table. My two inputs. And I'm going to stick to A and B. They've worked for me so far. I'll stick with them now. And over here, I don't have a special symbol. I'll make up one. A and 3 things like an equal sign except 3 lines instead of 2. A is equivalent to B, meaning they have the same value. And here we go. 0001, 1011. All possible inputs. Now, for me to be able to design this using my ands and ors and nots, I have to know its complete behavior for all possible inputs. And I want the output to be 1 whenever the inputs match. I spy a match here. They're both 0. I want the output to be 1. I spy another match way down here, and that's it. Those are the only places. So there. I'm designing a gate, so to speak. I'm designing a logic circuit, a digital logic circuit, that will perform just like an equivalence gate would if such a thing existed. So I'm not really building a gate. I'm using gates to build a circuit that behaves the way an equivalence gate would, and I'm way belaboring that point. Where do we go from here? Actually, I think we can write a fairly decent English description, can't we? Equiv, this will be equiv, so I can refer to it in my word description over here. Equiv output should be, this is an observation too. Equiv output should be 1 when one or on, I'll start talking in terms of on and off like light switches or something, should be 1 or on when A is off. If you'd rather write that as A is 0, that's okay. That comes directly from the table. I'm trying to translate it into an English description. Maybe I'm not doing a very good job. Equiv output should be 1, also known as on, when A is off and, whoops, there's an and B is off. And this one down here, and A is on and B is on. Now put that in quotes to make it look like some sort of official pronouncement. Equivalence output should be a 1, also known as on, whenever A is off and B is off. Both of those are off. And when A is on, well, there's a problem here. Ands. Remember, the only way and can be true is if everything involved is true. A and B is only true if independently A is true and B is true. So here's a problem. I can't have A is off and B is off and A is on and B is on. That's impossible. I can't have a switch that's both off and on. So this is worded poorly. This should not have been an and. This should have been an or. There's two ways. There's two ways I want to see one as output. One of them is if A is off and B is off, then I will see this one and that one only. There's no way I can see both of these ones in the output at the same time. I've either got the switches set so that I'm on this row way up here with A is off and B is off, or another possibility, if I see a 1, is that both of the switches are turned on, if I think of these as little light switches over here. So both the lights are off. My equivalence gate should be on, equivalence gate output. If both of them are on, my equivalence gate output should be on. And those are the only possibilities. Let me read this back, see if this makes any more sense now that I fixed it. Equivalence output should be on, or 1, whenever A is off, yes, and B is off. They're zeros. Or A is on and B is on. I think that'll do it. Well, let's see here. Rewrite, W-E-R-I-T-E, rewrite as a Boolean formula. A is off, not A. This little tiny little Boolean formula here is true whenever A is false. This is a 1 whenever A is 0. What about B? On that first row, B is off. Okay? So what I've got represented so far is not A, off, not B, off. And if I'm on this row, then that means both of these things are true simultaneously. Not A and not B. Think about that real hard. It might seem simple, it might seem hard, it might seem medium. Somehow or another, see if you can figure out exactly what's being represented right there. Not A. If A is 0, then not A is 1. I'll even write that down here. If we're on the first row, not A has value 1 or true. If B is 0, then not B is a 1. The dot means and. I'll have to put a dot because I didn't leave room to write and. But 1 and 1, that's actually the only place in the truth table for the AND gate that this thing would be true. Let me get the whole thing up here. That's one row. That little expression, that little Boolean expression right there, represents being on the first row. I want to see 1 in the output if we're on the first row. I want to see 1 in the output if we're on the last row. This one might be easier. Maybe I should have started down here, even though it would have been in the wrong order. I want to see this one in the output when A is on, just plain old A. And when B is turned on, just plain old B. I'll use blue for being down on the bottom row. Down on the bottom row, if A is 1 and B is 1, then clearly, I hope it's clear, that 1 and 1, that'll be 1. A and B in that case would be 1. Now, just as... No, Leo! Leo, no! Just as right here is this row, right here is that row, I cannot possibly be on both rows at the same time. I want the output of this entire operation here to be 1 if I'm here or here. And the way I represent being on the first row or the last row is with our, well, it looks like a plus sign, but it's the logical symbol for or. Okay? Leo distracted me. Sorry about that. Rewrite that as a Boolean formula. What was rewritten as a Boolean formula? This thing right here. So we could write this. If equiv is the name of this gate, I can just say equiv equals not A and not B or A dot B. Now, if you're taking notes, you run the risk of making a big mess if you try to write down everything I'm about to write down. Because I want to go through all the possibilities. This is the first time we've actually seen a Boolean logic formula for anything. But let's see if it works for all possible rows here. 0. If I fill in 0 for A and B all the way across, then I'll have 0 with a bar over it, dot, 0 with a bar over it, or 0 dot 0. That's equal to not 0. Not 0 is a 1. And not 0, that's a 1. Or, and those are still zeros. 1 and 1 is 1. 0 and 0 is 0. That's an or. We're not really adding. That's an or. 1 or 0, true or false, is 1. Now look at that. You can copy down if you want, but I'm going to go through that for all 4 of these different possibilities just to make sure, double, triple sure, that this formula works the way we want it to. Not 0's a 1, not 0's a 1. Plain 0, plain 0. Those are both zeros. When I do the math, the Boolean logic algebra math, I get the answer that I want. Check. You're done. Goes away. Oh no, we're not on the first row. We're on the second row, where A is 0 and B is 1. Fill in the blanks. A is 0, B is 1. Whoops, I wrote B. Silly me. B is 1. Or A is 0 and B is 1. Can't write and talk at the same time. All I did was replace A with 0, because I'm on this row right now, the blue row we'll call it. I'm on that one, and that's got A is 0, B is 1. A is 0, B is 1. I do some simplification here. Not 0 is 1. And not 1 is 0. Or 0 and 1. 1 and 0 is 0. 0 and 1 is 0. You had 2 chances and you failed them both. You're a 0. But that's what we wanted. We wanted the output to be 0 in that case. You know what? I said I was going to go through all 4 rows. I'll leave the other 2 rows as an exercise for you to convince yourself that we will, in fact, get 0 as the output for this formula when A is 1, B is 0. And we will, in fact, get 1 as the output if A and B are both 1. When the smoke clears, all we really wanted was that formula. I don't have an equivalence gate. Well, now I know how to make one. Here comes the fun part. I say that to get you excited about it. You might not think it's fun. I'll do it in purple. It'll be funner that way. Here's A. Here's B. Now it turns out, if you look at this formula, we need not only just whatever the A input is coming across here, and whatever the B input is coming across here, we also need some not A and some not B. And the way I do that is just break off a piece. That little dot there, when you put that on a wire when you're drawing a circuit, that's called a node. And all it does is just put a fork in the path here. So whatever A is, if it's a 1, there's a 1 going across this wire. But it also takes a turn to the south. And it's also coming along this wire. So if this is 0, that's a 0. If that's 1, that's 1. Okay, I'm belaboring that point. Why do I do that? So I can get hot and cold running A here. We get plain old A up here. This is not A. So I've got either one I need whenever I want it. Same thing with B. I need some plain B coming along this top wire. I might also need some not B coming this direction. And this is a standard way to do that. Especially when you get to more complicated formulas, you almost always need both versions of your inputs, the plain version and the inverted or the not version. Where do we go from here? Well, let's look and see. This says I want to feed some not A and some not B into an AND gate. Here's what an AND gate looks like. Remember, that's the semicircle, the half moon, whatever. Feed in some not A as one of the inputs. We always draw these with right angles, makes them look official. And digital logic simulators, they always use, well, they don't, but we'll say they do. Not B, I also need some not B. I'll label these. Since this is our very first one, this is plain A along that wire. This is not A with a bar over it along that wire. This is plain B along the top wire. This is not B down here. And if you look and see how I connected the wires, if I connected them correctly, then we've got not A coming in at the top and not B coming in at the bottom. Pink and purple. They're so pretty. Then what's coming out on the other side if that's the case? This, not A and not B, not A and not B. That was fun. Let's do this one. Plain old A and plain old B. Here's an AND gate. Now here's the rules. If I cross wires, it doesn't hurt anything. The only place where I have to worry about this electrical interference or whatever is if I've got a node there. In other words, I can feed plain OA as the top input in this by just crossing these wires like I'm not paying any attention to them at all. That doesn't look very good right there. Let me fix it. There. That little juncture right there, that's not a node. That's just there's not any way to draw the wires without crossing them, so that's what we got to do. So this is not any kind of interfered A, that's just plain OA. And I need some plain OB down here for the second half. Here's plain OB. Plain OB, plain OB, plain OB, plain OB. So if I've got plain OA and plain OB fed into an AND gate, then I've got A and B coming out the other side. That's not the whole thing. If this is going to be a constructed equivalence gate, then we've got multiple inputs but only one output. How do we combine these? Well, it tells us right here. There's the recipe. Look how this translates directly into a diagram that uses what we know about ands and ors and nots and everything. The bars translate into the not gates, the and stop talking and keep drawing pictures. They're all brought together into an OR gate at the end. This, that. What am I feeding in? Well, I'm not going to recopy it. It's close enough. The top input is not A or not B. The bottom input is A and B. So grand finale over here. The output of the whole thing is going to be that. If I've got room to write it, I'll have to write it in 2 rows. Not A and not B, or A and B. Also known as, down below, A is equivalent to B. Designed from scratch. Implemented with our logically complete and, or, and not. Now, if we were going to use this on a larger circuit, what we could do is just kind of split this off and say, you know what? I've got an equivalence gate now. I've designed that. We would do what's called black boxing it. We would say it's got these 2 inputs over here. It's got exactly the output I want. Well, how did you do that? Well, I did it. I mean, you can look at the technical details if you want, but you don't need to. All I'm concerned about is I've got 2 inputs, A and B, and my output is that A is equivalent to B. In other words, the output will be 1 if and only if A matches B. They're both zeros or both ones. I'll run through one of these. Will I? Is that a good idea? Yeah, let's just try it with one. Let's see. I wish I had some sort of dice or random coin tosses or whatever I could do. Let's do I'll use, well, I've already used pink. I'll use green. Let's try this out when A is 0 and B is 1, just to see what happens. Just for poops and giggles. Here we go. A, here comes the 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. There's a 0 going into that. What else? A goes into this not down here as a 0, comes out the other end as a 1. So there's a 1 going into the top input of the AND gate. I did that so quickly. Let me do that again. I'm pretending that the switches right now, for this instant, this one instant, A is a 0. So there's a 0 going across this wire, feeding into the top of this AND gate down below. There's also a 0 going into the NOT gate, coming out the other side as a 1. Because whatever you feed into a NOT gate, it comes out the opposite on the other side. So there's a 1 going into the top input of the AND gate up here. See how that works? B is a 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Goes 1 into the bottom of that AND gate, and I feed a 1 into this NOT gate. It comes out the other side as a 0. 0, 0, 0, 0, 0, 0, 0. AND gate. One of the inputs is a 0. That's enough. The output of the AND gate is a 0. Down here, AND gate, again, we've got a 0. If we have even one 0, then the output of the AND gate is a 0. 0 or 0 gives you nothing. 0. Is that what we want? Yes. We only want the output to be 1 if the inputs match and the inputs don't match. Done and done. We still don't have a Pentium processor, but what this is supposed to be is an existence proof. If we can dream it up and as something that we can represent Boolean logically, then we can design it using nothing but AND and OR and NOT gates. Check. An equivalence gate, or substitute therefore, thereof, therewith, heretofore. I'm going to quit while I'm ahead. See you online.